here we're going to discuss differentiability and what it means for a function to be differentiable. So we say f is differentiable, D-I-F-F-E-R-E-N-T-I-A-B-L-E. F is differentiable at a point if f prime exists at that point. This definition actually says two things. It says what I just said, reading the parentheticals and stopping there. I'll put a period there to make that a little less unclear. It also says a different sentence if you ignore the parentheticals. So we say f is differentiable if f prime exists for all x in the domain of f. So it can be read with the parentheticals, stopping here, and it can be read without. And they say slightly different things. The one says a function is differentiable at a point if the derivative exists at that point. The other says it's differentiable if the derivative exists everywhere in the domain. So a function will not be differentiable if the derivative does not exist at a point in its domain. And we'll see that in a moment. But an important result on differentiability is the following theorem. If f is differentiable, meaning differentiable everywhere in its domain, then f is a continuous function. A proof of this follows the definition of continuity with the limits. We won't cover that. I'm not too concerned with that. But this remark is much more of a concern for me. The converse of this statement does not necessarily hold. So this theorem says if f is differentiable, then f is continuous. True. The converse, flip it around. If f is continuous, then f is differentiable. False. It is false, and we'll show that with an example. So if a function is differentiable, then it is continuous. If a function is continuous, it's not necessarily differentiable, meaning if a function is continuous, the derivative does not exist everywhere necessarily. It could, but it's not guaranteed that a continuous function will have the derivative existing everywhere. And let's see that with an example, a common example that we have seen, but not lately. Well, in a 4-week course, I guess everything is lately. Although it could be argued in a 16-week course, everything is lately. Example. We're going to find a function which is continuous, but not differentiable. And remember, for it to be non-differentiable, the derivative must not exist at a point. It could not exist at a bunch of points, but all we need is one. F of x equals absolute value of x. The absolute value function is defined piecewise. And we will use the piecewise definition here. Absolute value of x is x, if x is positive or 0. And if the input is negative, then the absolute value is the negative of that negative. And we're going to show that this is not differentiable. To show it's not differentiable, we need to show the derivative does not exist at a point. We will show that it's not differentiable at x equals 0. And we'll show it a little informally. A more formal way of doing this is with the definition. I'm going to jump over that because I do not believe it is completely necessary, especially now that we have derivative rules. So our goal was to find a continuous function which is not differentiable. So let's observe. Where should we observe this? F of x is continuous. Why is it continuous? Well, let's just look at the graph. We can draw this without lifting our writing implement. I guess the way I did it, I didn't, but there. You can draw it without lifting or writing it. So it is continuous. If we show that this is not differentiable, then this serves as a counterexample to the converse of that theorem. So let's show it's not differentiable at 0. What does that even mean, not differentiable? Well, what does it mean for the derivative to not exist? All of the derivatives we've taken have existed. What does it mean for the derivative to not exist? Well, we have to go back to the definition of the derivative. The definition of the derivative is a limit. And the limit could exist. The limit may not exist. So here, we show that the limit does not exist. We're going to show it informally. We're going to show that the derivative on the left of 0, that's the right, we're going to show the derivative on the right of 0 is different than the derivative on the left of 0. So I'll say, how do I say this? Here we'll show f prime on the right of 0 differs from f prime on the left of 0. Again, this is an informal proof. A formal proof would go through the definition, but I'm going to do it informally because we can see it on the graph, or the function. Well, f prime on the right, f prime on the left. We have a piecewise function, which is conveniently split at 0. So note, f prime of x equals, well, we have a couple power rules. One, if x is larger than or equal to 0. What I just said is incorrect. It is not 1 at 0. It is 1 away from 0. Don't worry too much about that. We can't take a boundary point. But the boundary point doesn't matter because we don't care what happens at 0. We care what happens on both sides of 0. Derivative is 1 using a power rule. Derivative is negative 1 on this side. And 1 does not equal negative 1. So f prime on the right of 0 is 1. F prime on the left of 0 is negative 1. And because of that, as it goes through 0, the tangent lines are shifting from negative 1 to positive 1. When that happens, you can see that in the graph. Tangent lines here look like this. But once it hits 0, it does this flip the tangent line into positive ones. And that visual is actually a visual for lack of differentiability. A tangent line going from something like a negative to a positive. That tells us at this point the derivative will not exist. I'm going to make a remark. So this is the end of that example because we showed that the limit, maybe I should say, no, I'm not going to write it. I'll just say, therefore, the limit does not exist at 0. The limit which defines the derivative. I'm going to make one additional remark which might make this a little more clear. A curve which is differentiable is given here. Something like this is differentiable. Do I have a stick or a line or something? I do. I mean, a marker's just not big enough, or an eraser's not big enough. So right here, this curve is differentiable everywhere. This next curve is not. And we can see that with tangent lines. Before this video, I should have gone outside and gotten a stick, but I wasn't even thinking about it because I wasn't even thinking of doing this. Now, why is this differentiable? Well, let's take tangent lines, and let's just look at how they travel through this curve. Tangent lines travel like this, and then back up like that. So the tangent lines to this curve If you have this written down, you might be able to do this with your pen or pencil. Just let the tangent lines go, and notice these tangent lines just smoothly glide through this curve. What do the tangent lines look like here? Well, they're always tangent 1, or negative 1 on this side. So starting here, tangent lines, tangent line, tangent line. Once it gets here, it jumps from here up to like that. As it goes through 0, it on the left of 0 looks like this, and immediately on the right of 0, it jumps to a positive. And then the tangent line goes through afterwards. So this differentiable in higher math is frequently called smooth because of how these tangent lines kind of smoothly go through something which is differentiable, but do not smoothly go through something which is not differentiable. I'm not going to test you on what I just said about smoothness, but it's definitely a nice visual to have with the tangent lines kind of gliding across a function for a differentiable curve, but not for a non-differentiable curve. So this example, the absolute value, served as a counterexample to the converse of that theorem. Let's do, well, there are two other counterexamples. Let's just draw those, and I'll illustrate it with the tangent lines, just like this. Marker. The following remark. The following curves are continuous but not differentiable. Differentiable is a really long word. It's so you might want to abbreviate it just DIFF. The following curves are continuous but not differentiable. So all of these curves, there will be 3, will serve as converses to that theorem. 1. I don't need a Cartesian plane. Why would I need a Cartesian plane? Some curve that looks like this. Let's throw a Cartesian plane on it. Why not? Cartesian plane. A curve which looks like that. So the first one looks just like the absolute value, and it's not differentiable here because these tangent lines jump around. This one, not differentiable here, and this next one, we'll do one that looks like that. These could all have arrows. Will look like that. It's not differentiable here, although some may take slight issue with that. I actually never liked it, but it's a convenience thing. So here, it's not differentiable at this point because the tangent lines jump from this negative to a positive. What happens here with these tangent lines? Well, let's let the tangent lines travel through the curve. What happens here? Well, they go like this, like this, like this, like this, and they're approaching what? These are all negatives. The slopes of these are all negative because they're going downward. Negative, 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 all the way down to negative infinity. But what happens over here? Once you start here, well, maybe I'll do the same type of thing, approaching it from the right. Approach it from the right. Approach it from the right. Well, we have positive slope because it's going upward. Positive slope, positive, 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 and it approaches positive infinity. So down here, approaching negative infinity, over here, approaching positive infinity. So what that would look like going through that point is something like this, where it has to flip around like that. So this function, not differentiable here. This function, not differentiable here. This last one, it may look differentiable at first glance, but it actually isn't. Because you can actually see this kind of going through that like that. But you have to be a little careful with it. Because here, as we approach this point, we have positive slopes. Here, as we approach that point on the other side, we also have positive slopes. In math, sometimes infinity is inconvenient. And right here, this going to a positive infinity, and this going to a positive infinity, it is convenient in higher math to define something like that as non-differentiable. So for this class, we will also say that that's non-differentiable at that point. Right here, these all have names. Right here, a corner point is a point of non-differentiability here. A cusp point is a point of non-differentiability. And here, this is actually, at that point, there's a vertical tangent. At a vertical tangent, we have a point of non-differentiability. I would say, if I ask anything on these, I would stick with absolute value function or something with a cusp. But I think the visual is nice. The visual with the tangent lines is actually reasonably complicated. It's much more complicated than just going through tangent lines, but it's definitely something I would like you to, I'd like you to look at. And as we go through calculus, seeing how tangent lines travel through curves is actually very, very, very useful.